Hello, everyone. I'm Lila Zhang, a senior researcher from Microsoft Research. I'm glad to present our work here. Due to COVID-19, I will give a remote online presentation about our study on the popular vision transformers, which is aimed to empower vision transformer inference on mobile devices. Let's start. As we know, there is a large demand of DN deployment on edge and mobile applications, such as face recognition, on-device video analytics, VR and AR. In these years, CN models such as mobile-led V2 become the dominating model choice in mobile applications. Recently, we are noticing the fast development of new DN models, the vision transformers. They are built on the popular transformers, which is firstly proposed in NLP domain. This figure gives a high-level architecture of vision transformers. Unlike CN models take an image as the input, vision transformers split the input image into a set of patches. These patches serve as the input sequence and are treated the same as tokens in an NLP application. Then the model structures are very similar with transformers in NLP. Vision transformers usually are stacked with multiple encoder layers, where an encoder consists of a multi-head attention layer and a feed-forward network FFN layer. Today, various vision transformers have been proposed, and they surpass CN models with a higher accuracy in many vision tasks. However, the success of vision transformers comes with increasingly larger model size and computation demand than CN models. Compared to CN models, vision transformers have different operator and structures, and more importantly, the flops are much larger than CN models. Given the highly constrained resources on mobile devices, we ask a question: can we deploy vision transformers on mobile devices? Although there are works developing smaller vision transformers, the inference performance such as memory cost and latency have considered. Moreover, many characterization and benchmarking works for mobile devices focus on CN models. Therefore, there is a lack of comprehensive understanding of transformer inference behaviors on mobile devices. In our work, we present the first comprehensive empirical study of vision transformer inference performance on diverse mobile devices. Our work is a twofold study. Firstly, we give a systematic measurement of various models on mobile devices to understand the inference latency, memory cost, energy consumption, and the performance bottlenecks. Secondly, we further conduct multi-dimensional DN acceleration approaches on existing vision transformers to study the minimal achieved inference latency and the possibility of efficiently deploying them without redesign new models. We now start from the setup of study 1. As shown in Table 1, we collect a set of representative large and small vision transformers as well as 3 mobile CN models. They are used for performance baselines. Table 2 lists out the considered hardware and the corresponding frameworks. We studied 3 mobile CPUs, 1 mobile GPU, and an edge VPU. Unfortunately, we noticed that unlike CN models that have been supported by most of the mobile devices, vision transformers cannot run on mobile GPU and VPU. The reasons are unsupported operators and tensor shapes in vision transformers. Therefore, our studies are conducted on the 3 mobile CPUs. We first look at the memory footprint. This figure plots the memory consumption of both CN models and the vision transformers. We also report the parameter size of each model. We can see that the memory footprint is relevant to the size of model parameters, and the results suggest that for small transformers, they consume a same level of memory with CN models. But for inference latency, which is a crucial metric in deployment. There is a large gap between CN models and the vision transformers. This figure shows the inference latency on 3 different CPUs. From these latency numbers, we can see that vision transformer inference on mobile devices is extremely expensive, with 1.6 times to 41 times longer latency than CN models. Even for the smallest transformers, the tiny and T2T VIT7, which have a similar model parameter size with CN models, the inference latency is still 1.8 times and 2 times longer than in FissionNet on Pixel 4. We are curious about the reasons and latency bottlenecks, so we look at the layer level and operator level latency. We first count the latency for each type of layer. According to the functionality, we group layers into pre-post-processing attention layers and FFN layers. As shown in Table 3, except the T2T VIT, attention and FFN layers are the latency dominating layers. Compared to the attention layers, FFN layers are more time-consuming. We look at the latency percentages of each type of operators. As shown in the figure, we can see that MATMO is a latency bottleneck. Since vision transformer consists of a large amount of computation-intensive MATMO operators, the inference latency numbers are much larger than CN. For the final part in Study 1, we measure the energy and the power consumption. Our results suggest that the power consumption on mobile CPU is relatively stable. Different models consume a similar level of power. As a result, energy consumption highly depends on the model latency. Not surprisingly, CN models are the most energy efficient. The large transformers consume much more energy than CN models. To summarize our Study 1, we draw the conclusion that vision transformer inference on mobile devices is extremely expensive, and the large number of MATMO in vision transformers are the latency bottlenecks. We got the implication that we call new efforts to reduce vision transformer inference latency. To empower vision transformer inference on mobile devices, we need to reduce the inference latency. If we deploy the current models rather than designing a new model, we can consider the acceleration approaches to reduce the latency. In our Study 2, we consider 3 popular acceleration approaches and evaluate how they accelerate vision transformers and the achieved minimal latency. These approaches are operator fusion, which is to reduce memory cost, inter-8 quantization, that can reduce memory cost and accelerate hardware instruction executions, and structure pruning that reduce the computation and memory cost. Firstly, we evaluate how the operator fusion optimizes vision transformers. Operator fusion usually happens for a pair of one computation-intensive operator and one memory-intensive operator. The memory-intensive operator computation is fused into the previous computation-intensive operator. As a result, the memory cost and the latency is reduced. We start from the operator fusion detection method. We use the N-meter fusion detection method to do so. We select 2 operator pairs in CN and transformers. As shown in Table 4, in CN models, the 2 pairs are supported by fusion in both TF-Lite and TVM, and the latency is significantly reduced. However, in vision transformer, even the 2 operator pairs can be fused. None of the 2 frameworks support the operator fusion. Since our previous experiment suggests that Lelom and glue take relatively large latency percentage in small transformers, it's encouraged to support the fusion for speedup. We now evaluate the inter-8 quantization. It covers FP32 to inter-8 with minimal accuracy loss. Ideally, it can achieve 4 times the reduction in model size, memory, and latency. We conduct the inter-8 quantization on 4 vision transformers and compare the relative model size, memory, footprint, and the latency ratio to IP32. As shown in this table, we can see that int8 convolution largely reduces the model size and the memory cost, but hardly accelerates the inference of small transformers. T2T VIT7 becomes even slower at int8 convolution. To analyze the reasons, we look at the operator level int8 latency. As shown in the red part of the table, we found LLOM and GLUE are much slower after int8 convolution. Currently, only the Matmore accelerator can be significantly accelerated. The latency speedup for softmax is also minimal. Our implication is to further optimize the int8 convolution for LLOM and GLUE. Finally, we conduct structure pruning, which is aimed to remove the redundancy in models without a significant impact in accuracy. We use the state-of-the-art N-pruning algorithm, which is developed by Hugging Face. It prunes redundant heads in attention layers and prune channels in FFN layers. The pruned models are with much smaller size and flops. We conduct 3 experiments. Specifically, we study the redundancy in attention and FFN layers respectively, and with the observations, we further study the redundancy in the whole model to achieve the minimal latency. We first prune only attention heads for the dead tiny and dead small. As shown in this table, it suggests there is a large redundancy in attention heads. For the dead tiny, there are 3 attention heads in each encoder layer. We can prune 1/3 head with 18% latency reduction and only 0.75% accuracy loss. Then we prune only FFN layers. As shown in the figure, there are about 20% redundancy in FFN layers in the smallest data tiny. Finally, we prune both attention and FFN layers. We set different combinations of attention heads and FFN sparsity to prune. Our experiment results suggest we can prune 1/3 head and 10% FFN in each encoder layer. This results in a minimum of 0.75% accuracy loss with a 23.2% latency reduction. We also conduct int8 convolution to the pruned model, and the final model saves 32% latency compared to the dead tiny. Here are the key summary and implications by study 2 for the 3 popular acceleration approaches. Operator fusion is fully supported for vision transformers. Int8 convolution only significantly accelerates the Matmore operator and achieves small speedup for small transformers. Structure pruning is effective in reducing latency, but the compressed model latency is still 2.75 times of mobile LED V2 on Pixel 4. In another word, the compressed model for the smallest data tiny can be served efficiently on mobile devices. For the feature works, we think there are 2 promising directions. From system-level optimizations, we support operator fusion and int8 convolution. From algorithm-level optimizations, we call for design of more efficient models for mobile devices. In summary, we conduct a 2-fold systematic measurement study for vision transformers on mobile devices, which include a measurement of inference latency, memory, energy consumption, as well as the behind-the-performance bottlenecks analytics, and a study of how current acceleration approaches speed up the inference of vision transformers. We highlight 7 key findings. The real-world findings and implications can be used as guidelines for future vision transformer design and optimizations. Please read our papers for details. That's all for the talk. Thank you.